Okay. So what we have next is we know that we can pass some argument. Last time I showed you the use of quicksort. Well, actually I'm not showing the quicksort, but I'm showing the use of the generic pointer. Okay, so the generic pointer here is allowed you to accept anything. Basically, you can pass a string, array, or even just an integer, but use pass by reference so that you can pass it in to match this pointer type. Okay, so pointer type to pointer type. Now the problem comes, well actually this defect, kind of defect, is that every thread function, or by the design of the prefect create call, you can just pass one argument. So that means here is the only guy. If you want to pass multiple items, you may need to set up a structure. Okay, so you set up a structure and you pass a pointer to that structure, so that you can pass at the same time a lot of things. And just like what I've done in quicksort, I know that, oh, you are passing me a pointer. In this case, I pass you the character pointer, right? A string is a character pointer. I shouldn't say this, but a string can be represented by an address, okay? So this is an address, so I use a character pointer to receive that address, no problem. So I dereference it. No, it's not dereference, it's just casting, no dereferencing. In the quicksort example, I have dereferencing. Here, we don't need any dereferencing. We just cast it to the pointer type because we make use of the pointer type as a string, okay? And then print it out. So you will find a string. Why I don't write it in here? Let me highlight it here. Why I don't use a char type? Okay, it's because of the requirement of thread function. Thread function never designed for just one data type, but for generic purpose. Okay, generic means everything. All right. So this is an illustration. What happened while this example executing? I never execute this example in front of you, right? So I will execute now. Okay. So the prefect hello world.c. Okay, so I do this on purpose. You see this is a different program. So how different it is? Let's take a look at. I have main function here. I didn't show you the thread function yet. Okay, just take a look at the main. So the main will do the thread creation. You can assume that just like fork. Okay, when you call fork, you create a process, and the process goes in parallel. Remember, it's parallel. It's going in parallel with you. You are the parent, and the new one is child. Now, I want to show the same effects for threading. I call this thread main thread. Okay, so this is the thread that's running on the stay here. Okay, running the main function. So I call it main thread, and there is a child thread or the hello thread. Okay, so there's a hello function or the hello thread. Now I want to go to the hello thread function now. Okay. So the hello thread function is kind of a similar design here. So you will see I loop for many times. When some milestone comes, okay, milestone, let's say how many here? 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? 10 million, okay? So here is some milestone. So when I hit a milestone, I will print something. If you see a prefix t colon, that means it is from the hello thread, okay? The threading function is here. So what I'm going to show you, I want to show you is like this. You create a thread function. That function is not just let it run, and after it run, then the turns go back to the main. But I want to show you that these two guys run in parallel. Okay? So are you ready? Prefect hello world. Okay, let's go. So you will see that the main thread won't have the t prefix. So you see the pattern, huh? So what the pattern tells you? The pattern tells you something interleaving happens. The t appear first for this side. So this is the threading function, and after some time, the main function step in. Okay, so how many CPU I have? Okay, so first of all I have to show you CPU info. Okay. So for this computer, the first processor is 0. And can you find any processor name here? No more, just one processor. So I have one processor. So that means that even though I do it in a multiple process manner or multiple threading manner, although threading is hiding inside a process, you will see they in leaving just like sharing the resource of the CPU. Huh? So this time is, I don't know why, this time is a main thread one first and a hollow thread one longer, and then go back to the main. And what is hollow is by the end of the hollow thread, the last statement is saying that, okay, that means it's die. Okay, so you will see that they go in parallel. Okay, and I can tell you a little secret is for Linux, when you open a thread, actually it may go to different processes to run. Maybe you have a 2 processor or one processor 4 core, so they will go into different cores to run. Okay, so you will have an even more horrible result if your system has more CPU. Okay, so this is the output. Now let's go back to the simple example. The simple example is not very funny. It's just like the function call. How can I describe it as a function call like this? Okay, so the main thread start first. You start with a lifeline and then go down and execute one more. I consider a system call, okay, but actually it's not. So we call it a prefab library call. So prefab library call create a new thread. So the red guy comes in. So the red guy comes in, you will expect that it will start running. So it depends on how many processes you have. And what is this guy? I don't think that you remember last lecture I talked about this guy. This guy is actually the wait, okay? The wait PID or the wait. It will wait for what? You are the caller is the main, so that means that you are the parent, okay? Just like fork, okay? You are the parent, and parent say that I want to join somebody. Join whom? Join the TID. So who is the TID? TID is passed by reference, save the identity of this thread. Okay, so that means that it's actually the wait, and it's also happened in this program. Okay, sorry. Okay, so in this program, the main thread is here. I also call prefab join. Okay, so I can demonstrate to you what happened if I don't call prefab join, but later. Okay, so after prefab join, you will see the main thread terminated. So that's why you will always see, no matter how many times I run, the last printout message will be main thread terminated, because it will wait for the child thread dies. And here, if the main thread is not died, the child thread is not died, the main thread will block there. Okay, if the child thread die, main thread won't block and unfreeze and print this line. So this line is always the last guy. Now, what happens if I do this? Okay. I comment a prefab join. Okay? I don't join now. Just like in the fork scenario, we don't call wait. Okay? So let's see what will happen. So there are 2 points. This point is the main thread, not main thread, it's child thread. Child thread's last sentence. Okay? And this is the main thread last sentence. So they are the 2 milestones that you have to take care of. Now I run. Okay, this is a normal scenario. Try one more. I am always normal. Hey, come on, give me something abnormal. Wait. Okay. I have to do some tricks. Okay. Remove 2 zeros for the main. I have to make. Okay. Yeah, that must be abnormal, huh? Where is hollow? I removed 2 zeros, so it will slow down by 100 times. Okay? Only 1 over 100 times is needed. So you will see, just like fork scenario, fork you create 2 processes, you didn't call wait, your parent dies, so the prompts appear. But for the fork case, it's different, right? The fork case, you will see the child process keep printing things out. Okay? Where is the child thread? So this is the special things about prefab programming. Okay? Prefab programming is always, some people consider as safer. Okay? Why is it safer? Because you still remember what is the meaning of having main calling return 0? Main call return 0, what is the effect? Huh? What is the effect? Process termination, right? So if it's process termination, that means that all threads are just component of a process. All threads dies. Okay? So that's why in process type, okay, the multiprocess you call fork, no matter whether you have call waits or not, those data will be get processed, get print from a child, but here is not. So remember, this is a very important point. Some powerful stuff like return 0 here or exit will kill all the threads. Okay? So here you just terminate and the child thread is gone as well. Okay? So this is the prefab specialty. Any question you want to ask? Sorry, my voice is not that good. So I have to train all kinds of different things to tune a bit. All right. Then I show you a very critical and very important example here. Okay, so what is the critical example here? Critical example here is, of course, it's not just something like this. It's a kind of hard to you. Okay, so you have to pay your attention. Okay, if you need coffee, go to buy it. Okay, I don't know why this building don't have any coffee. Take a look at this program. So this program I will trace a little bit for you, okay, and show you this horrible phase here. So what this program is doing is actually create one thread, okay. From the main, it spawns a child thread, and child thread I usually call it do your job, okay. Do your job, and inside of do your job, what you're doing. Now take a look. You have this prefab create, and I said that you can pass whatever data type, okay? You can pass a string, you can pass a structure, okay? As long as it's a pointer, then and it's okay. So I will set integer here inside the main. Use its address, passes to the thread function. Okay, so the thread function is a new guy, right? You create a new guy, and the new guy receives the pointer and try to do what? Just like the demonstration that I used in the quicksort, I first cast it back from void asterisk, so the generic pointer, back to the integer pointer, okay, and dereference it to make sure that I receive 10 in this example, okay. So make sure I receive 10. Then after that, I update this by doing so from 10 to 20. Okay? So what will happen? An example here, I make it more funny. Okay? So I use a random number. Okay? I use a random number instead of 20. Yeah, just you expect that the effect is the same. Okay? Let's go. So you can see it from the file name, it's called evil. Of course, it's an evil demonstration. So from the main thread, the first time it says 10, no problem. Pass it to the child thread. I said that I will do the dereferencing. Dereferencing, where are you? Okay. Dereferencing here, okay, to make sure that I get the correct result. Good. Why good? You can see both of them saying 10. Okay, but something not very good happened. Inside the child thread, I updated to this number, 83. Okay, so why I can update it? I just do the same thing. Okay, dereference and put it on the left-hand side of assignment operator. Then I can update it through pointer arithmetic. After the guy has terminated, this guy is a thread. After terminated, I print out, I print out the last value of the input variable. Okay? Now remember, it's after the termination of the thread. Okay? But I got some bad news is it's 83. Okay, it's 83. So actually you may not understand what is the meaning. Okay, but using threading, especially using C++ and C threading, okay, C# no problem, Java no problem. So all kinds of old type of languages have no such a problem. The problem comes from pointer. Okay, so that's why I put eval here. Let's investigate what happened. Okay, and the investigation is very hard to understand. Okay, so first of all, this is an animation. Now you have to remember this, okay, or you write other threading program, you will have this problem. Now we have some memory, the code, the global variable, the dynamically allocated memory. I said it is shared among all different threads. Okay, now what happens when I create a variable, okay, variable inside the local variable? No problem. Just allocate some space in this orange area. Okay, so this is what happened while we call for help that I need a local variable. Okay. Then what is the meaning of? I don't know whether you know it or not. Okay. Do you know what is the meaning of having a parameter? Parameter is actually a local variable. Do you understand? You know about this, right? It's actually text space in the memory space, and a parameter is just another form of local variable. Okay? So I consider these two guys all own some space in the memory. This is his memory, the red guy. The blue guy also has his memory. No problem. Okay? But actually when I draw it in this way, it is just a misleading diagram. Why I say it's misleading diagram? Look at the type. Look at the type. This guy is an integer, 4 bytes. Okay? This guy, what is it? Generic pointer. Can be anything, but not some real memory, just a pointer. Okay? But if you understand what we call a indirect addressing mode, or the pointer will hack, okay, inside the assembly language. Actually, this is also something of 4 bytes in 32-bit CPU. So these two guys are 32 bytes, okay? So that's why I draw it this way. And the next thing is very horrible. What we are doing is actually parsing this array, address, I want to say address, okay? This address, pass it to this red box, and the red box carrying this address, and this address is actually pointing to stereo. Okay? In the previous high-level description that I talked about, I said that they have separate local variable zone. Okay? I didn't say anything wrong. Because local variable zone are separated, but actually they are inside the same process. Then what is the meaning? The meaning is that we can use pointer to go from one area to another area. As long as you give me the pointer, you give me the address. Then I can use the pointer to control things here. Or vice versa. I can do some calculations and predict, actually there is maybe some variable in this location. Let me change the thread variable. It is doable, okay? So now here, this is a pointer pointing to this blue box. So that's why when I update it here, in this red code or the new thread code, I'm actually modifying this guy, okay? So this is the true meaning of thread. Threading is an illusion, just an illusion that you think that, two guys running together without any interruption. No, you are actually sharing the same piece of memory. Okay, you are inside the same process, so that you can go to some dangerous space and do some damages. Okay, so then you will ask, hey, I know this problem now. Okay, I heard of this problem. Maybe you don't understand, but you heard of this problem now. How can we save our lives? Yeah, it's about parameter parsing, right? I always pass parameter, but when I pass parameter, you tell me that you cannot change the parameter. No way, right? You give me something, I want to change it, it totally makes sense. But demonstrate it is very dangerous that you will modify the things from the source. Okay, so this is the source. So what should you do? Okay, so it's illustration. What should you do? Then you should do the following. Okay, what is the following here? Although the file name is called evil. Okay, the following treatment is we call. I shouldn't use this word, but I kind of misleading. Okay, but you just hear it. Okay, I call it the thread data. Okay, kind of misleading because it's really not a thread data, just a share memory. Okay, but I set up a thread data. Okay, what is the thread data? I set up a local variable inside the thread function. Okay, and I immediately dereference it, copy to the ID variable. Okay, so that what? So that I don't need to go through the pointer to pollute this guy memory. Okay, because you pass me the pointer, I can pollute your memory through the pointer, but I want to avoid it and back it up. Okay, so what will you expect from this program? You will expect from this program now is beautiful. I do a for loop. Okay, every time what you're doing, passing the I variable address to the threading function. So the threading function will print out something. Is my ID number is something. Is 0, 1, 2, 3, 4. Okay. So after printing 5 numbers, I will join them. Okay. I will join it one by one. Okay. I don't know who terminate first, but eventually I can wait for the 0 guy, the first guy, and all the way down to the 4th guy, and 4 means the number 4, okay? Then I can finish the job. Now, show you the results. I love this program. This program is crazy. Okay, let's take a look. It says 0, 1, 2, 3, 4. Eh? Why always 5? Hey, come on, give me some variation. Huh? What? Let me try Mac. Mac maybe give me some surprise. Yeah, I didn't. Did I clone the project? No. Didn't clone the repo. Wait for a moment. I have to clone the repo first. Git clone. Okay. Maybe Mac give me some surprise. Evil 2. Ah, good. I love this. Can you explain what happened? 23355. Hey, give me something normal. Can you give me something normal? No normal things happen. Ah, yeah. How about Linux? Oh, always sucks. Okay, here, oh, at least I have some variation, okay. This is the best scenario I can have. Okay, at least we have 4 different numbers. Okay, so can you explain what happened? Can you understand what happened? What happened to this program? This program seems to be a kind of a fix, right? The fix is I back up, right? I'm doing a good things. Okay, you send me a pointer. Okay, I know pointer is dangerous, so that I back it up in my local variable inside my thread. The CPU, the Mac machine, the Linux don't agree with my approach. Okay, they give me some counter example. Okay, and take a look at the program as well. Okay, I modify the program a bit. I modified a bit. Okay. Oh, what happened? Always run out of battery. What happened? Okay, so I modified this loop a bit. Okay, so maybe I tune it back. I tune it back to the PowerPoint version. Okay, I equal to 1, 0, 5, I. Okay, so tune it back. no, this time it's different. After I change it, it's become different. Can you guess what happened? Can you think of any reason why it behaves like that? Yeah, you already know the answer. You have learned it in a scheduled chapter. It's about scheduler. Yeah, let me ask you. If I create a process, does it guarantee that it always start running? No guarantee, right? There's no guarantee that when you create a process, it will start running. Threading is the same. You create a thread, is it guaranteed that it will start running immediately? Of course not. Now, if you have this information in your mind, can you interpret what happened? Can you interpret what happened? Let's imagine it's like this. All 5 threads are being created, but never get the chance to run. So all 5 threads are already created, and then I will jump to line 12 to start another loop, and line 13 tell me that I have to be blocked until when? Until my target thread terminated. This is the wait, okay? So then what will happen if this is the case? The main thread start running, create all 5 threads. All 5 threads don't have any chance to run. And when they run, what is the result of I? What is the value of I in the main point, in the main function? I is equal to 0, right? I is equal to 0. Take a look at this result. Can you see 2 zeros here? Okay, these 2 zeros are actually 2 of the threads being created. Okay, they are created, but they don't have a chance to run. Okay, don't have a chance to run. Maybe, okay, I just interpreted maybe because I don't know whether this is the real first thread or my interpretation. My interpretation is like this. You create it don't have time to run, so the main thread start executing the next loop. Okay? And the next loop tell you that, okay, stand there, wait for termination of some thread. That's why I equals 0. And by the time you copy it to your backup variable, you are still, what happened to my factory? Huh? By the time you copied it, okay, you're actually following the pointer. Okay? So this is the problem. So writing thread has to be very careful. As long as you're using thread, you will face this danger. And don't get me wrong, you're using Java, you will also face this danger. You're using C++, you're using C#, you will also face this danger. Why? Think about it when you pass in an object. Yeah, do you know that copying object is not really copying? An object variable name equal to an object is copying reference. How about this? Is it copying reference? Just the same. Yeah, the same concept happened, and even harder to debug. Okay, in Java you trust it. Okay, in C# you trust it. Actually, you're being cheated for a long time. You may have this problem. May. Okay, here just like my example. For example, you may have a problem. Oh, this time it's always, okay? I don't know why, okay? Some years before, okay, my CPU is slower. Then sometimes I have a 0, 1, 2, 3, 4, okay? It's just sometimes, huh? But this time it's none of the case. This is the closest, okay? Mr. 1, okay? 0, 1, 2, 3, 4, Mr. 1. Okay, so remember, this is not just a C problem, even though you do the backup. The previous case is the backup is actually just a fake, okay? Why I say this is just a fake? Because you didn't really solve the problem. You still relied on a pointer and rely on the time that you use that pointer value, okay? So what is the solution? What is the solution? Using threading is kind of a disaster because you have to be very clear about the concept, just like writing JavaScript, okay? I'm teaching another course teaching JavaScript. All people being KO by me is showing some example. You think that is correct and it's actually wrong, okay? So just like that. C is also like that. Threading is particularly hard, okay? So here is another example showing a bad example, and the solution is very easy. The solution is, how about I don't pass in the same address for the 5 threads. I create 5 different variables. Then problem solved. Okay, so this is the source of the problem. That guy, okay, this symbol is the evil source. We remove the evil source, okay? Make sure that when you pass in the pointer, you set up 5 different pointer value or 5 different variables so that you pass in different values, so that I don't care whether you have backup or not. If you don't back up, you change the value in the main. If you have backup, okay, you are still using something good as long as no one will change you. Okay, so the solution will look like this. Or maybe I use this. The font is better. To solution. Okay. Yeah. So I set up something, a global variable. Maybe you choose another variable, it's okay. I choose global variable. Maybe you choose a local array, no problem. Okay. I just treat an array as the data that I want to pass in. And then I say that, okay, this is global I, make sure that I pass different address to the thread function. Okay? So make sure that you don't step in this tricks, okay, this trap in C#, in Java, because you may pass in object. Then you will try passing in object reference. Then you are actually passing the same objects, but you use different variable as the reference. Okay? So here is the same. You use the same variable for different threads, but actually the same pointer. All right. Yeah, this is the disaster, okay? And now we go over the disaster, we'll go into some good parts, okay? So the good part about the prefab programming is it accepts return value, okay? Let's say you process something, you can return something back, but again, it's using generic pointer, okay? This is particularly useful, like you want to do some maybe, okay, you imagine that this is a simple thread. This thread is sent to a GPU to do a processing, okay? I don't know whether you have processed GPU or not. GPU is just like the same concept here. You pass in an array, pass in a lot of data, okay? Actually, what it is doing is compute a number and give you the back number, okay? So here is just the same. You do a lot of things, maybe you do some computation. The computation in this example is not important, okay? It just complain about something, okay, that if you don't put a pointer here or don't do this casting here, you will have a big problem, okay? It will go all the way wrong, okay, and we keep on complaining you. So make sure that if you want to use it, copy my example here, then you won't get any trouble, okay? And one more problem is about the malloc, okay? I don't know whether you have solved the, what is that? One more exercise, right? Exercise 1, I issue that to you guys, okay? There is a problem talking about returning a local variable of a function, okay? Do you remember that? No one remember, okay? I don't have to show it, okay? Just remember there's a problem, huh? You return a function has return value, right? You return the function, but the return value is actually the local variable address, not local variable value. You cannot return local variable address. Here is the same. You cannot return the address of output variable, but you can use malloc to create a piece of memory, save it here, and return it to the outside world, and tell the outside world that, hey, I do some changes in global variable, okay? Please take it, okay? Make sure that you understand, because later on this program, not I don't say this program, but this problem will come back when we talk about memory. Okay, when we talk about memory, I will also give you a challenge. Hey, okay, why I cannot return a local variable address? Then you will understand more. Okay, so thread scheduling. Thread scheduling is a easier part. Okay, we have something called green threads. So what are green threads? Let me show you the Wikipedia page first. Yee? Stupid Microsoft. It's supposed to be a URL, huh? Yeah, I'm not that crazy. I'm making it blue. Huh? Green threads. Stupid Microsoft keep crashing. Okay. Why not green threads? Sorry. Here. Okay, so what is green threads? Okay, I don't know whether you are good at understanding the background of the .NET framework, the Java VM framework. Okay, do you know that when you run Java program or any .NET framework program, actually they are not directly touching the CPU. Okay, it's passed through a machine, and the machine is just an executable. Okay, executable is a program. Huh? You give the code, the compile code of Java code, of C# code, and give a guy, and that guy will do the translation for you. Okay? Now the problem comes. That guy can translate many things. You say printf, okay, it translates to machine code for printf, okay. But how about threading? Yeah. Think about it. If that guy want to do the translation for you, does it mean that he have to pretend that itself is a kernel, right? Because he pretends to be a guy to interface with the thread, okay? So the green thread implementations is actually means don't treat it, oh, green is good, green computing, whatever, yeah, it means sucks, okay? It means less resource. That's why it's a green, okay? Less resource without a kernel interruption. All the threading is emulate, okay? It's emulate, or some even is pretend to be a thread, okay? A JavaScript is good at that, okay? JavaScript is actually, I don't know whether you know it or not. How many of you write JavaScript? No one. Heard of JavaScript? Okay, good, thank you. Okay, yeah. So you know JavaScript can allow you to register for a click, okay? And then you click later. As if there is a thread waiting for you, right? You click and suddenly, boom, there is a thing pop up, but it never interrupts the normal execution for the web page. It seems that it's parallel, running in parallel. But no, JavaScript is following even a worse model, not green thread, but one thread. Okay, it's a one thread kingdom. And here is a green thread. So what are the green thread kingdom? Take a look. They are family member. Ruby, yeah, Ruby before some version is green thread. Who know Go? No one know Go's, okay. Erlang, no one heard of it. D, I don't know D, okay. Limbo, what is that? Lua, Lua is a sexy language. What else? Smalltalk sucks. What else? Stateless Python. What is that? Oh, I don't know about this. Okay. So some of the languages, maybe you heard of it, maybe you don't heard of it, is implementing green threads. So what is green threads actually? It really exists, right? You take a look at the name. Even the Go proposed by Google. Okay, it's also implementing green threads. Green thread means that the kernel space never knows that you are implementing threads. Okay, kernel don't know. You call a prefab call, okay, prefab creates. Inside which system? Very old Unix. Inside old Unix, you can compile, prefab, create, no problem. But actually, it is emulated inside user space. Kernel don't know about it, and you will only receive. Well, this is the easier thing to understand. You will only receive one scheduling chance, and within that scheduling chance, you have to serve 3 threads. Okay, so that means Someone has to do the scheduling inside the process for you. Sounds very horrible, right? You don't want it. I implement thread, I have to implement scheduler. Okay, crazy. So it's not just as easy as that. The most difficult to understand drawbacks is, how about one of the threads, so-called thread? Let's say calling some blocking system call. Okay, blocking system call. That means you go down to the kernel level. The kernel don't think that you should continue to run. You have to wait for something. One thread calling it will hold hostages of all threads. All threads have a block together with you. Okay, so it's totally fits the multi-threading purpose. That's why you cannot see the nowadays operating system here. But you can see modern languages who go through some so-called virtual machine of implementation, like Ruby. Ruby has its own interpreter. Python has its own interpreter. Go also has its own interpreter. They will go through the interpreter. The interpreter think that, let's go through this model. Then stops. How about the latest model? Latest model is what we call a one-to-one model. Means that the kernel knows there is this thread. Okay? You call prefect create. Actually, you call system call to tell kernel that, hey, I want to launch a new thread. Okay, please give me a new thread. And give you a new thread means the previous drawbacks are gone. You will receive, for each thread, some scheduling quantum. Okay, so that means it's not one quantum given to all threads, but each thread has its own quantum. Some threads run more CPU resources, then you will be having, like, how can I explain this? Just like queuing, right? You use up your quantum, you go back to the queue, okay? So other threads don't use up, okay? You will still inside the chance to have the chance of being selected by the scheduler, okay? And other variance is the previous case when a guy call a blocking system call. Let's say this guy called blocking system call sleep, okay? It won't block the remaining two guys. And this is the modern model. So the Linux, the Mac, the Windows all implement this, okay? And what is the drawback? The drawback is actually very interesting, okay? I don't know whether you observed this or not. Let's try, okay? You know, I can do a fork program. Let's choose a fork program. What is that? Part 1, okay. Process, simple fork program, okay. Hey, what is that? This fork program is not very good, huh? Hey, I should have some very simple fork program. Okay. So you can see this PID just stay together, right? This is something that you may have observed during the time that you do assignment 1, okay? Now, what I'm going to say next. Actually, inside the Linux implementation, because you want to have a thread pretend to be known by the kernel, so the easiest way to implement it is upgrade it to be a process. So that means what? That means there is some bad thing. The bad thing is, can I call fork inside thread? Is it safe to fork within a thread? Yeah, you should ask this question, right? What will happen? To the high level point of view, it is a thread. Low level point of view, it is a process. So a thread is totally qualified to call fork. But what would happen? Actually, I don't know. It depends on system, and also there are things that you can define. What happens if a thread called fork is totally okay from a low-level point of view, because it's just a process. And why previously I showed you the PID? Okay, actually, those thread takes ID. Let me show you. Let me remember what is that. It's called PSELF. Let me see, ELF. Wow, the list is so long. What happened to my machine? Okay. So this guy, LWP, lightweight process. Okay, this column is a thread ID. Okay, this is thread ID. This is the PID. So what is PPID? Parent ID. Okay, parent, yourself, and the thread. Most of the case, you will find the thread ID is equal to your PID. Right? Now let's see some other example. Okay, go to some big numbers. Let's pick this guy. What can you say about this? What is this column? Still remember? PID. This column, PPID. This column, thread ID. What can you say? The highlight process that I put in the screen is just one process. 3 threads. The 3 threads taking 3 different IDs, and this ID cannot be others process PID. Can you find any 20x0 in this column? And this is already sorted, so you cannot see it. Because it silently take a process ID to pretend to be a PID. The TID, okay? Thread ID, okay? So that means what? That means I'm actually explaining this. Okay, this I use English to type it. It's not very good. I should just program to type it. This means you are actually spending extra resource. It seems that thread is not occupying PID, right? The thread is a thread, okay? You occupy PID, so that means it's just like what we have previously, the zombie factory. Yeah, you are taking up some resources, but without your awareness. You can create, you remember that, oh, maybe I can create 1,000 process, okay? But actually you cannot create that much because some process create threads, and the threads takes the IDs away, okay? So it's also take away some process control memory inside the kernel, okay? So this is a much more expensive but worth solution. Worth in the sense that it's really give you the high level of consistency. So that's why all the supercomputer is implemented this way. Okay. So you know that I take part in that competition. What is that? ASC 201 something. Yeah. Is it? No. Oh, it's gone. Oh, the competition is gone. Thank you. Okay, the supercomputer competition. Okay, so actually we have to think of ways to have a good threading scheduling, to have a threading memory allocation down to that level to do optimization. Okay, so that's why I kind of understand this kind of, okay, because I always guess about it. Yeah, don't hack the kernel. Let's just try to get through it and get the qualification, go to finals and eat the dinner. That's all. Okay. So here is the illustration. So if you have an old model, so it will become something like this. There is a so-called threading library, just like Java, just like the old Ruby, just like the stateless Python. Okay, they are all having threading libraries inside a process to do the threading. If it's not, then the scheduler, we call it thread-based scheduler, the scheduler knows who are you. And since the kernel version 2.6 in Linux, that means more than 10 years ago, okay, we are changing from process-based scheduler to thread-based scheduler. Okay, so it's already a good scheduler nowadays. Okay, wow. We are going to a tough part now. Okay, I think we need a break. Okay, during the break, let me show you a video. Okay.